Imagine you could leave Earth right now. No spacecraft limitations. No fuel constraints. Just you, moving outward through space at the speed of light. You'd pass the moon in about 1 second. Mars would blur past in 4 minutes. And then something strange would happen. The distances would stop feeling like distances. They would start feeling like something else entirely, like silence, stretched thin across an ocean with no shore in sight. You would travel for hours, then days, and the sun behind you would shrink to a bright star among stars. And you still wouldn't be close to the edge. That's the thing nobody tells you about the solar system. It is almost incomprehensibly large. And its true boundary, the place where our sun finally lets go of the universe, is so far away, so strange, and so poorly understood that scientists are still arguing about where exactly it is. This is a journey to that edge. Not a metaphorical one. A real, scientifically grounded voyage from the warmth of Earth to the absolute frontier of everything our sun has ever touched. And what we find out there will fundamentally change how you think about where you live. Most people have a picture of the solar system in their heads. 8 planets. A few rings. Maybe an asteroid belt somewhere in the middle. Everything neatly arranged on a flat disk, color-coded for easy identification, orbits perfectly circular, the whole system fitting comfortably on a poster you'd hang in a classroom. That picture is almost entirely wrong. The real solar system is a dynamic, violent, sprawling structure that extends not millions, but trillions of kilometers from the sun. Its outer regions are inhabited by objects we've barely catalogued. Its boundaries are defined not by rock or ice, but by invisible forces, magnetic fields, particle winds, the slow gravitational grip of a star that is, by cosmic standards, completely ordinary. The solar system isn't a neat diagram. It's a vast, largely unexplored wilderness. And the further out you go, the stranger it gets. So let's move. Starting from the beginning. Earth sits about 150 million kilometers from the sun. Astronomers call this distance 1 astronomical unit, 1 AU, and it becomes the measuring stick for everything that follows. At this distance, sunlight takes about 8 minutes to reach us. The temperature is perfect for liquid water. The magnetic field shelters us from the worst of the sun's radiation. We live in a rare sweet spot, and we almost never think about it. Leave Earth and head outward. You cross the orbit of Mars at about $1.50. Already the sun is noticeably dimmer. The warmth you take for granted on Earth is fading. Mars receives less than half the solar energy we do, which is part of why its surface is frozen and its atmosphere is barely there. A thin ghost of what Earth's feels like. Continue outward and you reach the asteroid belt, a ring of rocky debris between 2.2 and 3 Australian dollars and 20 cents. Popular culture imagines this as a dense, dangerous field, ships weaving between tumbling boulders. The reality is far more boring and far more interesting at the same time. The asteroid belt is mostly empty space. If you collected every object in it and compressed them together, the total mass would be less than 4% of the moon. The rocks are separated by hundreds of thousands of kilometers. You could fly through the asteroid belt and probably never come close to hitting anything. But these rocks matter enormously. They are leftover material from the solar system's formation, frozen in time, preserved like ancient fossils. When we study asteroids, up close with missions like OSIRIS-RX or from the ground, we are reading the original recipe of our solar system, the ingredients that existed 4.6 billion years ago before planets had fully formed. Some of these asteroids contain organic molecules, amino acids, even water-bearing minerals. The building blocks of life, drifting silently in the void between Mars and Jupiter. Keep moving. Cross past 5 Australian dollars and suddenly, everything changes. Jupiter. Nothing prepares you for Jupiter. Even knowing the statistics intellectually, encountering the reality of this planet is staggering. Jupiter contains more mass than all the other planets in the solar system combined, more than twice as much. Its Great Red Spot, a storm that has been raging continuously for at least 350 years, is wider than Earth. Its magnetic field is the most powerful planetary magnetic field in the solar system, extending millions of kilometers into space and creating a magnetosphere so large that if you could see it from Earth with the naked eye, it would appear larger than the full moon in our sky. Jupiter is not just a big planet. Jupiter is a gravitational force of nature. It has spent the last 4.5 billion years acting as a kind of cosmic shield, its enormous gravity capturing or deflecting asteroids and comets that might otherwise have bombarded the inner solar system. Many scientists believe that without Jupiter, life on Earth might never have had the stability it needed to evolve past simple microbes. We owe more to this cold gas giant than we often acknowledge. The Juno spacecraft has been orbiting Jupiter since 2016, and it has revealed something extraordinary. Jupiter's atmosphere is not a simple layered structure. It has massive cyclone clusters at its poles, dozens of storms arranged in geometric patterns that have no clear explanation. The interior of Jupiter is not well understood either. Models suggested a small rocky core, but Juno's gravity measurements suggest something far more unusual, a diffuse, fuzzy core that may stretch across nearly half the planet's diameter. Jupiter may have formed differently than we thought. And if Jupiter formed differently, that changes everything about how we understand the rest of the solar system's birth. Saturn appears at about $9.50. You might think, after Jupiter, that Saturn would be underwhelming. It is not. Saturn's rings, made mostly of ice particles ranging in size from tiny grains to chunks the size of a house, are simultaneously one of the most beautiful and one of the most mysterious structures in the solar system. The rings are astonishingly thin relative to their width. They span nearly 300,000 kilometers from edge to edge, but in most places they are less than 100 meters thick. That ratio is roughly equivalent to a sheet of paper spread out over a city. The rings are young, dangerously young in cosmic terms. Recent estimates suggest they may have formed only 10 to 100 million years ago, long after the dinosaurs appeared on Earth. Before that, Saturn was just a plain, ringless planet. And current measurements show the rings are disappearing, slowly spiraling inward under the influence of Saturn's magnetic field, raining icy particles down into Saturn's atmosphere. In another 100 million years, the rings may be gone entirely. We exist in the precise cosmic window where they can be seen. That is either a remarkable coincidence or a reminder that the universe is constantly changing around us, and most of that change is invisible to any single generation. Uranus and Neptune wait further out, at 19 and 30 Australian dollars respectively. These two worlds were long considered simple, cold, blue, distant, unremarkable. But they are the least understood planets in our solar system. We have visited each of them exactly once, with Voyager 2 in the late 1980s, and we have not been back. What Voyager revealed was tantalizing and incomplete. Uranus rotates on its side, its axial tilt so extreme that its poles point almost directly at the Sun during parts of its orbit. Neptune hosts the fastest winds in the solar system, exceeding 2,000 kilometers per hour, despite receiving almost no solar energy to power them. Both planets contain vast quantities of water, methane, and ammonia under enormous pressure. And at those depths, theory predicts something almost impossible. It rains diamonds on Neptune. The extreme heat and pressure in the interiors of these ice giants can break apart methane molecules, releasing carbon atoms that then compress and crystallize, falling through layers of liquid as diamond crystals. It sounds like science fiction. It is basic thermodynamics applied to conditions we struggle to even simulate on Earth. A planned mission to Uranus in the 2030s, currently the top priority of the Planetary Science Decadal Survey, may finally give us the data we need to understand these worlds properly. But Neptune at 30 Australian dollars is still not close to the edge. We have barely begun. Beyond Neptune lies a region that for most of human history was purely theoretical. The Kuiper Belt. Stretching from about 30 to 50 Australian dollars, it is a vast disk of icy bodies, remnants of the outer solar system's formation. Pluto lives here, reclassified as a dwarf planet in 2006, a decision that generated more public controversy than most actual scientific discoveries. But Pluto is far more interesting than a naming dispute. When the New Horizons spacecraft flew past Pluto in July 2015, after a journey of 9.5 years, scientists expected a dead, cratered world, a frozen relic. What they found was alive with geological activity. Pluto has mountains made of water ice that tower 3,500 meters high. It has a vast, smooth nitrogen ice plain called Tombaugh Regio, the famous heart shape, that is geologically young, perhaps only millions of years old, meaning some internal process is still resurfacing it. It has a thin atmosphere of nitrogen, methane, and carbon monoxide that rises and falls seasonally as Pluto moves in its 248-year orbit around the Sun. It has possible evidence of a subsurface ocean. Pluto should not be this interesting. By the thermal physics of its distance from the Sun, it should be utterly inert. The fact that it isn't is a mystery we haven't fully solved. The Kuiper Belt contains hundreds of thousands of objects larger than 100 kilometers across, and perhaps trillions of smaller ones. It is a second asteroid belt, but made of ice instead of rock, far larger and even more poorly mapped. And it is not perfectly stable. The gravitational influence of Neptune constantly nudges objects in the Kuiper Belt, sending some of them plunging inward toward the inner solar system. Short-period comets, those that return every few decades, like Halley's Comet, originate here. The comets that streak across our skies and have marked the calendars of every human civilization in history are Kuiper Belt refugees, gravitationally exiled and falling toward the Sun after billions of years in the dark. Past the Kuiper Belt, something even stranger happens. At around 50 to 100 Australian dollars, the structure of the solar system becomes increasingly chaotic and mysterious. This is the region scientists call the scattered disk, a zone where orbits are wildly eccentric, where objects travel in paths that carry them far above and below the plane of the solar system, where the gravitational order of the inner solar system has completely broken down. Objects here have been disturbed, scattered, sent on long, strange journeys by close encounters with Neptune billions of years ago. And then there is Sedna. Discovered in 2003, Sedna orbits the Sun at an average distance of about 500 Australian dollars, with a highly elongated orbit that takes it as far as 937 Australian dollars at its most distant point. At its closest approach to the Sun, Sedna is still never closer than 76 Australian dollars. This means Sedna is never close enough to be significantly influenced by any of the known outer planets. Its orbit makes no sense given the planets we know about. Something must have shaped it. Something massive, either a passing star billions of years ago, or, and this is where it gets extraordinary, a planet we haven't found yet. Planet 9. The hypothesis of a ninth major planet in the outer solar system has become one of the most exciting and contested ideas in modern planetary science. First proposed seriously by astronomers Konstantin Batygin and Mike Brown in 2016, the idea is based on a strange clustering of orbits among objects in the outer solar system. Several distant, trans-Neptunian objects have orbits that are aligned in ways that simple probability says should not happen randomly. The odds of the alignment occurring by chance are estimated at less than 1 in 10,000. The best explanation, according to Batygin and Brown, is a planet roughly 10 times the mass of Earth, orbiting the Sun at an average distance of perhaps 400 to 800 Australian dollars on a highly inclined, elliptical path. Such a planet would take between 10,000 and 20,000 years to complete a single orbit. It would be so faint that our best telescopes have not yet spotted it, but it might be detectable, particularly with the Vera Rubin Observatory's New Sky survey beginning in the mid-2020s. If Planet 9 exists, it completely rewrites our understanding of the outer solar system. It would explain Sedna. It would explain the orbital clustering of dozens of other objects. It would raise profound questions about how this planet formed. Was it born where it is now, or was it flung outward early in the solar system's history by a close encounter with Jupiter or Saturn? And it would mean that for all of recorded human history, there has been a major planet hiding in the darkness just beyond our perception. But even Planet 9, if it exists, is not the edge. At distances of roughly 2,000 to 100,000 Australian dollars from the Sun, Astronomers believe there exists a vast, nearly spherical shell of icy objects. No one has ever directly observed it. Its existence is inferred entirely from the behavior of long-period comets, those that take thousands of years to complete a single orbit, arriving from all directions, not just from the plane of the solar system. Something must be their source. A reservoir, storing trillions of icy bodies, slowly sending occasional visitors toward the inner solar system when nearby stars, molecular clouds, or the gravitational tide of the galaxy nudges them inward. This is the Oort Cloud. It is, arguably, the most extraordinary structure in our solar system, precisely because it is the one we know the least about. The Oort Cloud is theorized to contain between 1 trillion and several trillion icy bodies. Its inner edge may begin around 2,000 Australian dollars from the Sun, but its outer edge may extend as far as 100,000 Australian dollars, nearly 2 light-years, reaching almost halfway to the nearest star. At those distances, the Sun is not the dominant gravitational influence anymore. Objects in the outer Oort Cloud are weakly bound to the Sun, susceptible to perturbations from passing stars, galactic tidal forces, and other influences entirely outside the solar system. The Oort Cloud is where the solar system ends and the rest of the galaxy begins. Or is it? There is another boundary to consider. A different kind of edge. One defined not by gravity or ice, but by particles. The Sun constantly sheds material. Charged particles, mostly protons and electrons, stream outward in every direction at speeds of 400 to 800 kilometers per second. This is the solar wind. It fills the inner solar system, interacts with planetary magnetic fields, causes auroras on Earth, and extends far, far beyond the planets. But the solar wind doesn't go on forever. At some point, it collides with the gas and dust of interstellar space, the material that fills the galaxy between star systems, and it slows. This transition region is called the heliosheath, and the point where the solar wind finally stops, where it can push no further against the interstellar medium, is called the heliopause. The heliopause is real. We know this because we have crossed it. In August 2012, after 35 years of travel, Voyager 1 became the first human-made object to pass through the heliopause and enter interstellar space. The data it sent back was stunning. Within days of crossing the boundary, instruments detected a sharp increase in galactic cosmic rays, high-energy particles from outside the solar system that had been blocked by the heliosphere, and a corresponding drop in solar particles. The transition was sharper and more distinct than many scientists expected. Voyager 2 followed in November 2018, crossing the heliopause at a different location and revealing something surprising. The boundary is not the same thickness in all directions. The heliosphere is asymmetric, shaped by its motion through the galaxy, pushed in and stretched out, like a bubble moving through water. The heliopause sits at roughly 120 Australian dollars from the Sun, well inside the Kuiper Belt's outer edge, well inside the Oort Cloud's theorized location. This means the Sun's particle environment, the heliosphere, ends far before the Sun's gravitational influence does. There is a shell of space, from roughly 120 Australian dollars to perhaps 100,000 Australian dollars, that is gravitationally part of the solar system but is already, in terms of particle environment, part of interstellar space. The solar system doesn't have one edge. It has many, depending on what you are measuring. Voyager 1 is currently about 160 Australian dollars from the Sun and still transmitting data from interstellar space. Still powered by its nuclear decay battery, its signal taking more than 22 hours to reach us traveling at the speed of light. Engineers can still communicate with it. Scientists are still learning from it. But its power will run out around 2025, and then it will continue drifting, silently, on a trajectory that will carry it past the star Gliese 445 in about 40,000 years, at which point it will be closer to that star than to ours. Voyager 1 is not a spacecraft anymore in any practical sense. It is a message in a bottle, thrown into a cosmic ocean so large that the bottle will drift for tens of thousands of years before coming near anything else. Think about that for a moment. The fastest object we have ever launched from Earth, carrying the most optimized trajectory engineers could devise, using gravitational assists from the giant planets to fling itself outward. That object has been traveling for nearly 50 years, and it has crossed only the innermost, trivial threshold of the solar system's true extent. To reach the outer Oort cloud would take Voyager 1 not decades, but tens of thousands of years. To reach the nearest star system, Alpha Centauri, at its current speed, would take roughly 73,000 years. Space is not just big. Space is big in a way that human intuition is genuinely incapable of grasping without assistance. And yet, here is where the story turns. Because understanding the edge of the solar system isn't just an exercise in astronomical humility. It has direct, urgent implications for some of the biggest questions in science. Where does life come from? One of the most compelling hypotheses in astrobiology is panspermia, the idea that the building blocks of life, or even simple life forms, can travel between planetary systems carried inside comets and asteroids. If this is true, the Oort cloud becomes extraordinarily significant. When the Sun passes through molecular clouds or comes close to other star systems, events that happen on timescales of millions of years, the outer Oort cloud is disturbed and objects can be exchanged between solar systems. We may have received comets from other stars. Other stars may have received comets from us. The interstellar comet Oumuamua, detected in 2017, was the first confirmed interstellar object to pass through our solar system. Its trajectory, its shape, and its strange non-gravitational acceleration have generated more scientific debate than almost any other astronomical observation in recent memory. Was it a comet? An asteroid? Something else entirely? We still don't have a definitive answer. But its passage told us something profound. Objects do travel between star systems. The space between stars is not empty. It is filled with travelers. What shaped the outer solar system? The current orbital architecture of the solar system, the specific positions, masses, and inclinations of the planets, is not inevitable. Early in the solar system's history, the giant planets moved. They migrated. Models like the NICE model and the Grand Tack hypothesis suggest that Jupiter once moved inward, then outward, that Neptune and Uranus may have switched positions, that a period of intense bombardment in the early solar system may have been triggered by gravitational instability among the giant planets. The Oort cloud itself is believed to have formed during these early chaotic migrations, as billions of icy bodies were flung outward by close encounters with the giant planets. Understanding the Oort cloud, its structure, its population, its distribution, tells us about the violence of the early solar system. It is an archive of the most chaotic period in Earth's history, written in the orbits of trillions of icy bodies too far away for us to see directly. Is there life in the outer solar system? Saturn's moon Enceladus, at about $9.50, shoots geysers of water vapor and organic molecules into space from a liquid ocean beneath its icy crust. Jupiter's moon Europa holds a subsurface ocean containing more liquid water than all of Earth's oceans combined. Even farther out, Titan, Saturn's largest moon, hosts a complex organic chemistry on its surface unlike anything else in the solar system, with lakes and rivers of liquid methane, complex molecules raining from its orange haze. The outer solar system is not the dead, frozen wasteland we once imagined. It is populated by worlds with liquid water, organic chemistry, and possibly the conditions necessary for life. We haven't looked closely enough yet, but the missions are coming. Europa Clipper, launched in late 2024, is on its way to Jupiter's moon Europa. Dragonfly, a rotorcraft lander, is being built to explore Titan in the 2030s. The edge of the solar system is not a destination. It is a mirror. The further out we look, the more we understand about what's happening here at the center, on the small warm world where we live and ask questions. But perhaps the most important thing the outer solar system teaches us is something harder to quantify than orbital mechanics or comet chemistry. It teaches us humility in the deepest sense. We are here, on this planet, around this star, surrounded by a vast, mostly unexplored wilderness that extends for nearly 2 light-years in every direction. We have sent a handful of spacecraft. We have taken a few photographs. We have made dozens of theoretical models and confirmed maybe half of them. The solar system we think we know, the neat, poster-friendly version with 8 planets and some rings, is a cartoon, a placeholder, a story we tell ourselves because the real story is too large and too strange to fit in any single image. The real solar system is a place where diamond rain falls through the crushing interior of distant worlds, where trillion-object clouds drift in the near-interstellar dark, nudged occasionally by the gravitational tide of the galaxy into long journeys toward the sun's warmth, where interstellar travelers pass through without stopping, where a hidden planet may be circling the sun right now, tens of thousands of AU out, in darkness so complete that we haven't even noticed it yet, where 2 small spacecraft, launched before most people reading this were born, drift silently through interstellar space, past the reach of the solar wind, carrying golden records with music and mathematics and greetings in 55 languages. Improbable ambassadors from a species that has existed for an eye blink of cosmic time, already reaching, already curious, already unwilling to stay home. We are at the very beginning of understanding where we live. And that, in its own quiet way, is the most extraordinary thing of all.